Thank you very much for the introduction. And as you just heard, we are going to look at the humidity and clouds in the upper troposphere and the processes that control these clouds. So why are we interested in the UTLS? So this is a schematic from an overview paper by Andrew Gattelman from 2011, and I guess most of you have seen this, but I just want to bring it up again to kind of set the scene. So we are talking about this transition layer between the troposphere, where we have a lot of clouds, high humidity, and a stratosphere, where we are governed by more dry dynamics, much longer timescales. And here you can see here in the blue shading, this what some people call exotropical transition layer, mixing layer, UTLS, there are various terms around, but it's this transition layer around the 2 PVU isoline, where these two reservoirs of air are in contact and in exchange. And this is a particularly interesting region because it's the coupling between those two different reservoirs of air, and there is a lot of processes going on from the very small scale turbulence to baroclinic wave breaking. So a very large range of processes that control what's going on in this area. And therefore, we are quite interested to understand the coupling of those processes and how that controls the distribution of, for example, water vapor, but also other chemical constituents across this layer. So I already indicated that there is a huge gradient in humidity. So this is exactly from the same time and location as this previous snapshot, but now error 5, a profile of specific humidity. And you can very well see that this is mapping or following more or less the 2 PVU isoline. It's not exactly a 2 PVU. We see kind of also enhanced values in some regions above the 2 PVU, but mostly the high humidity values are found in the troposphere, and likewise are clouds mostly. If you look at the representation of humidity in this critical layer in current state reanalysis data sets, you find actually issues. I want to illustrate this with a recent paper by Konstantin Krüger et al. From the DLR, where they look at profiles of humidity from error 5, which you can see here in the red line, and then from observations from a specific from halo dial, so remote sensing observations on board the halo. They are shown here in the black line. And we can see that, well, far away from the tropopause, so note this is tropopause relative altitude that you can see here on the y-axis, we see that they actually agree reasonably well. We see the sharp drop across the tropopause, or a bit above. And then we see around 2 kilometers, we see a relatively large bias. You can also plot this as a bias instead of just comparing the two lines, and we see that this peaks in about 1 kilometer above the local tropopause, reaching up to a layer of maybe 3-4 kilometers above the local tropopause. So this is, of course, not known and not nice. This has been known for some time now. This has also been a problem in error interim, actually. But why should we be concerned about this? Well, this has implications because the water vapor at that altitude range is really crucial for the radiative processes, and the larger scale dynamics, and thereby the climate state as we represented this model. So on the left-hand side, you see a by now fairly old figure from Martin Ruiz's paper, where he looked at the radiative effect per change of in relative units of water vapor. And you see this peaks right at the tropopause. So right in the sensitive region, we have the strongest signal from any change in water vapor. This is most pronounced in the tropics, but we also see this extending to the extratropics. A more recent paper from last year by the group of Felix Plüger, they also showed with some model experiments that actually if you fix this bias in the UTLS humidity, that has implications for the temperature profiles, but then also the strength of the jet, for example, so what you can see on the right-hand side. So this is an area that seems to be really sensitive, and therefore it's also of so much concern if we get humidity in this layer wrong. This is also of concern if we talk about water vapor feedback in a changing climate, because we know that there will be changes in upper tropospheric humidity, and in particular, these regions will be very sensitive to changes. So what controls humidity in this layer? Well, on the one hand side, this is large-scale transport. So this is a schematic from an 10-year-old paper by Zahn et al. And that shows you a part of the extratropical UTLS, which will be the focus here, and the different large-scale circulations that impact the distribution of humidity in this layer. So coming from the tropospheric side, this is mainly the warm conveyor belt transport, so transport associated with extratropical cyclones, which was viewed as rather slow slantwise ascent. But then, of course, also deep convective system that transport air very rapidly from the planetary boundary layer to the upper part of the troposphere. We then also have some lateral transport from the Hadley cell mixing in of moist air that has been transported to the upper part of the troposphere in the tropics by deep convection. If you look at the stratospheric side of this transport barrier, there's an impact, or we see moisture transport of dry air by the different branches of the fluoropsin circulation. And so it's really this convergence of different circulations in the area that shape the amount of humidity that we have available, but also the gradients. So from the tropospheric side, warm conveyor belts and convection are the two key drivers to bring humidity up from the source regions at the land surface, the ocean surface, to this location. And then what happens within this layer is actually also influenced by clouds due to mainly to radiative processes. It has been known for quite some time, or it's very obvious that there is cloud top cooling from long wave radiation at the top of, for example, the outflow of warm conveyor belts, but also from deep convection. And this can actually lead to PV modification. If we go along with this definition of the dynamical tropopause, or the transport barrier between those two reservoirs, as a 2 PVU isoline, then of course any PV modification that happens in the vicinity of this isoline matters. Just to illustrate that this actually is something that we need to probably understand much more deeply, this is a profile taken from the CloudSat radiative heating product combined with ERA5 to derive PV tendencies. So this is now using cloud microphysical properties from observations, vorticity from reanalysis to derive PV rates. And this is just a random CloudSat profile taken, I think, in 2017. What you can see is that we see very large tendencies. So this is per second, located right next to the 2 PVU tropopause. And this is particularly the case here around 60 degrees north. This is actually one conveyor belt outflow, but this also happens very often within tropopause folds. So this is an indication that actually this is a process that may be important, and we don't very well understand it. Plus, additionally, of course, local radiative heating has impacts on stability and potential turbulent mixing processes. Okay, so but this won't be the focus of today's presentation here. I'd much rather focus on the moisture transport in warm conveyor belt and convection. We will look at the climatological perspective of the warm conveyor belt contribution to the extratropical UTLS humidity. And then we will look in detail at one case study of a warm conveyor belt and one case study of a deep convective system to understand more about the properties of the cloud system that impact how much humidity and how many hydrometeors arrive in the UTLS. So let me start with a formal definition of the UTLS. So if you go through literatures, there is actually various, often very vague definitions. And so if you want to do a quantitative study, we need to settle on an objective definition. What we decided to do is to look at the layer around the dynamical tropopause, where PVU is Lagrangian 6, and we extend to 50 hectopascal below the dynamical tropopause. Of course, these are numbers that you can pick them others-wise, but if you look at cross-sections and so on, this seems to be a reasonable definition. So on the left-hand side, we can see how this pans out for a specific situation. And in the lower right panel figure, you can see the climatological distribution over 10 years of era 5 for the Northern Hemisphere. So in principle, it does what we wanted to do. It captures this layer around the tropopause. Well, we now want to understand what warm conveyor belts contribute to this, and we focus on warm conveyor belts because we believe that at least the dynamics of these systems are reasonably well captured in existing reanalysis, which may be more questionable for deep convection. We base our climatological analysis on the years 2010 and 2019 and era 5 at 0.25-degree resolution and 1 hourly time steps. What we do with this is we compute forward trajectories and then look at large-scale ascent. So large-scale ascent is defined as air parcels ascending at least 600 hectopascal in 48 hours, plus they have to happen within vicinity of a surface cyclone. So you can see on the right-hand side, you can see 2 exemplary trajectories that do this ascent from the planetary boundary layer to the upper troposphere. And note that in comparison to existing studies on warm conveyor belts, we actually extend those trajectories until the continuous ascent actually stops. And this turns out to be really important if you want to look at outflow properties, because just using the 600 hectopascal ascent criterion often gives you points somewhere not very well defined in the middle of the ascent. So if you look at the distribution where we find those outflow air masses on a map, so the position of the trajectories where the purple star is, then we see they are centered in the storm track regions of the Northern Hemisphere. So we didn't look at the Southern Hemisphere, but for the Northern Hemisphere, they peak in the storm track region. So no surprise here. If you look now at the profiles and the anomaly in the total water content at the positions where we have warm conveyor belt outflow, this picture emerges. So again, we look at tropopause relative coordinates, and in the tropospheric part, so where the altitude is negative, we see this red-blue pattern, which means that warm conveyor belts actually have enhanced total water content compared to the background. The background here is actually defined as those regions where we on average see warm conveyor belt outflow. So we don't take, for example, Siberia into account in the computation of the background. We also see some pattern above the tropopause extending quite high into the stratosphere, and I'll comment on this in a second. I just want to show also the picture for specific humidity. We see now an emergence of a triple structure, so indicating that actually it's not only specific humidity that's transported, but the hydrometeors play here a crucial part, at least at the point of the end of the ascent. Finally, I want to show you here the temperature anomaly that goes along with in this column in the tropopause relative sense. And this is very strong temperature shift between the warm conveyor belt outflow and the background. And this is exclusively down to a shift, a climatological shift in the tropopause altitude. So in warm conveyor belt outflow, the tropopause is locally pushed upwards, which produces this cold bias that we see here. And using this actually translates to the signal in the stratosphere, and this temperature shift of the local tropopause actually explains this signal that we observe in the stratosphere. So if you do this in a not tropopause relative, but for example, a pressure coordinate system, the signal in the stratosphere is completely gone. Okay, so we now have shown that warm conveyor belts actually contribute quite a lot of humidity to the upper troposphere, and that this is significant on a climatological scale and impacts the background. So how long does this actually last? So how long do those parcels that arrive as warm conveyor belt outflow, how long are they actually anomalous in terms of their moisture and hydrometeor content? So for that, we extended all the warm conveyor belt outflow trajectories by another 2 days, so 48 hours. You can see the position where they arrive at the end of these 2 days on the map that I just brought up. And we can see that in general, they propagate southeastward. So the eastward is not a big surprise, obviously, in the exotropics. The extent to which they actually move southward, I found a bit surprising, but yeah, this is what happens. If you now look at the evolution of the total water content in the outflow, which is shown by the thin red lines and the shading, compared to the average or the background. And the background here is taken as all grid points, so at the same grid points, but from all the samples at this location that are not warm conveyor belt outflow. So the background is kind of moving with the Lagrangian paths of those parcels, but for the background and not the warm conveyor belt area. And so what we can see is that if you look at the median, then we see that after about 12 hours, the signal is actually lost. And yeah, in a Lagrangian sense, these parcels are even drier than the humidity, than the background conditions. If we focus only on the trajectory staying within 4 kilometers of the dynamical tropopause, so not the ones that actually do descend very strongly into the subtropics, we see that the signal lasts a bit longer, maybe 48 to 24 hours if you look at the interquartile range instead of the median value. So this is another thing that I found quite surprising, because I at least always saw this from conveyor belt outflow as this long stationary feature, you know, that hangs around quite a long time in the upper troposphere, which of course, if you look at satellite pictures is true, but in a Lagrangian sense, actually air passes move pretty quickly through this. So we are talking here about roughly a day. Okay, so warm conveyor belts contribute moisture to the atmosphere. That moisture hangs around, but is also transported out of the troposphere, of the UTLS again. So we wanted to make this a bit more quantitative in the sense of quantifying the flux of water vapor that we really get into the UTLS. So we again used trajectories to do these computations. Now we use domain filling starting from the UTLS. What you can see on top is the entire mass flux, and then on the lower, in the middle panel, the total water vapor flux, the total water flux into the UTLS, and at the bottom, the hygrometeor water flux. So we can see that the water flux, unsurprisingly, kind of mirrors the mass flux. So we have large mass flux. We also see large water flux. We also see that we have actual peaks over the storm track regions in the water flux, also the hydrometeor flux. But we also have some local hotspots along the subtropical jet, particularly in the Mediterranean and yeah, Himalayan region, and also Central Pacific. But so this is the total water vapor flux, and of course this does not include convection, because we can't see convection with trajectories in ERA5. This is the water vapor flux that we get from all processes, and of course not everything is warm conveyor belt flow. So to get an estimate of the warm conveyor belt contribution to this, we applied again our selection criterion from warm conveyor belts to this flux calculation, and then you can get the percentages of the contribution of warm conveyor belt to those fluxes. And depending what metric you're looking at, I'm just picking total water here, we can see that in the storm track regions, this is a substantial contribution of about 5 to 20% in the Pacific storm track. So this is quite a substantial contribution from warm conveyor belt alone. And note, this only includes the 600 hectopascal ascent. We know now that there is a lot of ambient air that does not quite make the 600 hectopascal ascent, but also contributes to water flux. Okay, to sum up this first part, warm conveyor belt constitutes the source of UTLS humidity and hygrometeors. I guess you all knew that, but we now quantify that. The warm conveyor belt outflow passes staying within 4 kilometers of the dynamical tropopause have a positive humidity anomaly for 18 to 24 hours. And the warm conveyor belt outflow contributes to 20 to 30% in the hydrometeor transport into the UTLS and about 5 to 10% for the total moisture. Okay, so these systems are important, but what actually controls how much moisture they are transporting upward? For that, I want to first show you a few results from a high-resolution model simulation that we did for a warm conveyor belt. So you can see the specific warm conveyor belt that we're looking here in this picture. The blue-white shading shows you the cloud, total cloud cover. We did some high-resolution icon simulations with a resolution of 3 kilometers, roughly 3 kilometers in the WCB ascent region, so where we think resolution is most important. We use double moment microphysics, deciphered in Bayesian scheme, and we use online trajectories. So these are trajectories that are computed during the model simulation and are propagated forward at each model time step, including integrating microphysical and other rates as we go along. So we get very accurate integrals. We do the same exercise. We identify from those trajectories the warm conveyor belt trajectories with a similar criterion. So you can see here two representations. What is quite striking is that actually we get quite a range of different timescales which they ascend. So you can see here the length of the red segments in the left trajectory. So this minimum time they need to ascend 600 hectopascal. And this is actually far from this slant-wise smooth ascent over 48 hours, 1 to 2 days. Instead, we see, at least in this case, and this is the autumn case, a peak in ascent timescale around 10 hours. So rather rapid ascent. I just want to keep you, for you to remember those two colors. So the blue one, the convective one, ascending in about 5 hours, less than 5 hours. So you probably would call them more deep convection trajectories than actual warm conveyor belt, but they are embedded within the larger scale warm conveyor belt structure. And then those with ascent timescales larger than 20 hours, more consistent, I guess, with the picture of large-scale smooth ascent. Okay, so how does the distribution of moisture look when they start in the Manu layer? So you will see now a number of these plots. On the x-axis, on the y-axis, there's always the variable of interest, and on the x-axis, there is this ascent timescale. So convective trajectories are on the left side of the plot, and smoothly slantwise ascending are on the right side of the plot. If you just look here in the top plot at the total humidity, so this is the red line, the black line that you can see on top in this figure, that shows you that actually trajectories that rise convectively start off with a bit higher total water compared to the slantwise. And this is because they are essentially happening at the southern side of those cyclones instead of the more northern trajectories that start closer to the surface cyclone center. This is actually mirrored quite nicely by the temperatures you can see in the lower plot. How has the picture actually changed by the time we reach the end of the ascent? So the purple starts again along the trajectories on the right-hand side. So we can actually see that the slantwise trajectories, they transport more total moisture to the UTLS compared to the convective ones. So despite we have this gradient in the inflow, we see it actually reversed during the ascent. We wanted to quantify this a bit more by using the so-called Lagrangian triangle ratio. So the ratio of the precipitation to the initial humidity. And you can see this picture, and it's of course is consistent with what I showed you before. So the very fast trajectories, they are actually most efficient in removing moisture, removing almost everything, and then the slow ones are actually a bit worse in removing. Although the numbers are here, they're generally very high. So note the y-axis is all above 90%. We also see some indication of a dip towards the very short time scales. We can further quantify the different processes that contribute to this. So one is removal by mixing with other air masses that are in vicinity, but also with other warm conveyor belt air parcels. And we see that this contributes about 10 to 20% of the moisture loss. And I found this also quite large, to be honest, but this seems to be very robust. We also see this tendency of increasing moisture removal with increasing ascent timescale, which we think is simply a manifestation of those parcels having longer time to mix with their environment. The other component is, of course, the removal by precipitation, which is shown on the lower panel. Again, this is very high, meaning that almost all the condensate that we form is very efficiently removed. We again see a peak of the efficiency around 10 hours, although here it's really a plateau at some shorter timescales. We can dig further into the microphysics by quantifying how much of the moisture is actually condensed. And here we see actually this gradient that we find in the total drying ratio. So slowly ascending trajectories are worse than strongly ascending trajectories in removing or producing condensate, converting moisture to condensate. And then we see the gravitational removal, the precipitation efficiency on the lower figure, which is actually pretty flat. So these are all very efficient in converting the condensate to precipitation. Although I must say that the pathways by which this happened, they differ quite strongly between the slantwise and the convective trajectories. And if you want to know more, I suggest looking at the paper as soon as we have submitted this. So what controls the humidity and the outflow? On the left-hand side, you can see a scatter plot of the humidity that we find in the outflow on the x-axis. And on the y-axis, the humidity that we would actually expect given the temperature and the pressure at the outflow position. And you can see that this is a very strong correlation with rather little scatter, which suggests that actually the specific humidity in the outflow, at least in the ICAM model, is entirely controlled by thermodynamics. If we look at the relative humidity over ice, we also see this. We have a very strong peak just right around 100%. Although now we already see a bit of a difference between the convective and the slow ascending trajectories. So in the convective trajectories, we have this very strong peak just below saturation and with respect to relative humidity over ice, whereas in the slow trajectories, we have this broader peak that is just centered slightly above 100% relative humidity. How do the hydrometeors look like? So this is ice. So we see here that the slow ones transport a bit more mass to the UTLS compared to the convective trajectories. This goes very well along with this increased precipitation efficiency, a slight increase in precipitation efficiency that we did observe towards shorter ascent timescales. If you look at the ice crystal number concentration, which is of course of relevance for the further evolution of these cirrus clouds, we actually see the opposite. So the convective ones, they tend to have quite much larger ice crystal number concentrations compared to the slow ones. If you look at the further evolution, so we have here only 24 hours because then the simulation stopped and we don't get enough statistics. We can see it on the left-hand side, the ice mass. This is dropping slowly, as you would expect from sedimentation. If we look again at the slow trajectories and the median, we see that we have a much more rapid drop-off than in the convective ones. And the current hypothesis is that this has to do with the ice crystal numbers. So if you look on the right-hand side, we see that the crystals, we have much fewer crystals here, so about 2 orders of magnitude, or 1 order of magnitude if you look at the mean, and maybe half an order of magnitude if you look at the median. And that gives you just larger crystals in the slow ascent than in the convective ascent. And again, the ice crystal number is going down as we would expect from sedimentation. Okay, let me summarize this in-depth view on one conveyor belt moisture transport. So the initial boundary layer moisture is actually tied to ascent velocity and the outflow temperature, and this has very strong implications for the specific humidity that it can actually transport there. The ascent timescale controls very efficiently the moisture removal. Specific humidity and the outflow seems to be very strongly temperature controlled, and there's very little wiggle room for the microphysics. However, we see larger spread in the hydrometeor mass and number concentration and outflow, which is also strongly dependent on the ascent timescales, and which has implications for further evolution. Okay, so I have spent now quite some time looking at one conveyor belt, so the slantwise ascent, although we see that actually there are elements of more convective transport in this, at least for the transition season systems. But how actually does this picture look like if you look at the deep convective event? For that, I want to show you another high-resolution case study that we also did with the ICAM model. You can see here the system in question. So it's a supercell storm that produced 2 to 3 centimeter hail in the Munich area in 2019. We did again high resolution icon simulation, this time having a resolution of or a grid spacing of 1 kilometer, I should say. We again use the double moment microphysics scheme. We again compute online trajectories to follow the parcels through the deep convective ascent. And we use the TOBAC code for cell tracking to actually focus on the individual deep convective storms. So what can you do with the online trajectories and these deep convective storms? So this is, for example, at one time step, the position of the air passes that are just about to ascend in this deep convective system. So you see this nice curved form, which is because this is right at the position in the storm evolution where we have the two updraft scores splitting. We can then look where the parcels were located 1 hour before they started the ascent in the boundary layer. And so we get the spatial map of what air actually makes it in the deep convective core, at least in the model, of course. And then we can look 1 hour later and see where this kind of dispersed to. And we kind of see this feature of spreading out horizontally that we would expect in the upper troposphere with a bit a shift given the background wind velocity. If you look at the altitude evolution, which I didn't show you, you can see this here. So the inflow for the system is mainly happening below 3 kilometers altitude. And then we find the outflow, between 10 and 13 kilometers, which very well matches with the local tropopause. I should maybe say 1 or 2 words on how we selected those trajectories. So we selected trajectories that did rise within the storm mass that was determined by TOBAC based on column maximum vertical velocity. And then we only retained trajectories that had a sustained vertical velocity of 1 minute more than 3 meters per second. So these are really the ones that go up through the deep convective core. And I think this is mimicked here by this altitude distribution. If we now look at the trajectories, the vertical displacement against the loss in moisture that they experience, you get this kind of histogram. So you can see roughly the higher trajectories rise, the stronger is the moisture loss. So again, this is not surprising. But if you look at the specific vertical displacement, we see quite a large spread. We can now do this in terms of drying ratio. And again, we see a very strong spread according to where actually, for a given vertical displacement, we don't see just one drying ratio, but we see quite a range of values. So 1 being meaning all moisture is removed, and 0 meaning actually we arrive with the same moisture than we started with. For the following analysis, because I really want to focus on this transport from the boundary layer to the UTLS, I remove all the trajectories that don't ascend more than 6 kilometers. And so we see these 2 plobs in the drying ratio here. So ones that are very efficient and then the others which are not. And of course, this is kind of very interesting. And that's why I looked at the vertical velocity that they experience during the ascent. And what you can see here is a histogram of exactly this column of the maximum sustained 1 minute vertical velocity for these 2 different boxes. And what is very interesting is that we find actually much higher velocities for those trajectories that have a lower drying ratio. And this means that actually those trajectories are very poor in removing moisture, most likely because the condensate is just not able to fall out because of the high vertical velocities. They just transport everything upwards. This is actually confirmed if you look at the hydrometeor content at the outflow level, where we also see substantially higher values in those trajectories with the low drying ratios and the large vertical velocities. If you look at specific humidity, the signal is not as strong. It's still a bit there that they carry more specific humidity. They actually also have a bit higher relative humidity over ice, but the main signal actually comes from the hydrometeors here again. If we now look again at the temperature control of the specific humidity in the outflow, you can see here the scatter plot of specific humidity in the outflow against temperature. We see for a very large fraction of parcels down to 220 Kelvin, we see again this very solid line, very tightly constrained to the thermodynamic maximum. And then we see this large spread for colder temperatures. And this is an indication that at least in this deep convective, at least in the model in these deep convective systems, the outflow of specific humidity is not as strongly temperature controlled as we did observe in the warm conveyor belt. Let me summarize also the conclusions that we have so far for moisture transport in deep convection. And I show you here on the right-hand side a similar diagram that you have seen for the warm conveyor belt before. We have the SN timescale, not the tau 600, but the actual SN timescale in the deep convection here. And this ranges from 10 minutes to 3 hours. And the trying ratio, and if you remember, actually, for the warm conveyor belt, we stopped at 2 hours because we couldn't go to higher resolution, and we were at this plateau. And now here, we definitely see this loss in the efficiency of moisture removal if we go to the very short SN timescales. So we see less efficient moisture removal compared to warm conveyor belts, particularly for the very small SN timescales. The maximum velocity and the SN timescale very efficiently control the gravitational removal of hypermeteors and therefore the hypermeteor mass in the outflow. There is still a temperature control on the outflow specific humidity, and although it seems much less tight than in the warm conveyor belt. And again, the high updraft velocity parcels stick out here. So this brings me to the summary of the entire talk. So we looked at UTLS humidity and hypermeteor distribution that is transported up by warm conveyor belts and deep convection. We did see both systems do actually have an impact, at least for deep convection in a case study-based approach. We see that actually for both systems, the SN timescales is a very good variable to quantify and control the efficiency of moisture removal. We find a maximum removal efficiency for timescales of around 5 to 10 hours with decreasing efficiencies in both directions, so faster SN timescales and slower SN timescales. The specific humidity in the outflow seems to be very strongly temperature cold, at least in the model, although there is some evidence of a less tight control for the very short SN timescale. The hypermeteor content in the outflow is very strongly contingent on the SN timescales and the precipitation formation and vertical transport patterns. What we're currently doing is actually trying to verify this with observational data, because of course there is a lot of question when it comes to the microphysics representation in the model. And I'm particularly a bit suspicious on this very strong temperature control of the specific humidity in the outflow. And we're currently trying to work with observational data to verify or disprove what the model is showing here in terms of water vapor transport. So with this, I'd like to conclude, and I'm really looking forward to your questions and the discussion.